Now we're going to use the relation we worked out for how the density matrix changes in time. This depends on the Hamiltonian. Now, we know our unperturbed Hamiltonian for our two-level system, and we know the perturbing Hamiltonian from our applied oscillating electric field. So we're going to be able to understand what the density matrix is as a function of time.
So we want to know what happens to the density matrix in time, because that's going to tell us what is happening to our system. Well, we know this relation that tells us how the density matrix changes in time that we deduced before, and we have our definition for our 2 by 2 density matrix here, and we know our perturbing Hamiltonian and our unperturbed Hamiltonian to give our total Hamiltonian. So we can use this relation, writing it out explicitly. Rho here doesn't depend on any other variables other than time, so we can simply make this a total derivative of time. And hence we multiply these various matrices together as given by this expression. So we can multiply that out and add everything up, and we'll leave that as an exercise. But this is the result of these two multiplications and the subtraction in here. We get this 2 by 2 matrix with these elements in it. Well, let's take the 2, 1 element of both sides, for example, in this expression we just deduced. So that will be d rho 2, 1 by dt, and writing that h bar omega 2, 1 will be defined to be E2 minus E1, then we can write this expression out here for d rho 2, 1 by dt. It's the 2, 1 element of what we see on the right, second row, first column. So that's everything that we see here. And we can simplify that a little bit using our definition to get this expression here. From the diagonal elements in this equation we had, so these elements here and here, we can examine the population difference between the lower and upper states. Remember, we understand that the population difference from our basic understanding of the density matrix is indeed just the difference of these two diagonal elements. This is the population in state 1, this is the population in state 2, relatively speaking. Well, the density matrix is Hermitian, which tells us that rho 1, 2 is equal to rho 2, 1 star. So adding these two together with a minus sign, so rho 1, 1 minus rho 2, 2, so this one minus this one, gives us this expression here, using also this relation. Solving this equation then, and this equation, will essentially tell us everything that's happening with this system. We will understand what's happening to rho 2, 1 and also rho 1, 2 because they're related by a simple complex conjugate relation, and we'll understand what's happening to the difference of the populations here. Note incidentally that we are not performing perturbation theory here. Within our approximations in setting up the model in the first place, this is an exact pair of equations for this system. So it will continue to work even for large values of E. We're not presuming only small changes to the system. Even though we talked about a perturbing Hamiltonian, we're not actually presuming that that perturbing Hamiltonian is necessarily small. So this is not a perturbation theory. This is apparently a complete description of this physical system, at least within our overall setup of the problem.
As we indicated before, so far everything in these equations was in the original time-dependent Schrödinger equation. Solving that separately for each of the possible pure starting states of interest, then averaging the resulting expectation values for some quantity of interest, such as the dipole moment, gives the same results as we get from our density matrix analysis so far. A key benefit of the density matrix approach is, however, that it enables us to model additional random processes that lie outside the idealized problem, and about which we may know relatively little. The simplest model for handling such processes is to introduce what are called relaxation times. This model is somewhat arbitrary, and it's a significant simplification of what could be very complicated interactions with the rest of the world. It works very well, however, in many situations, and is therefore very useful.
Consider a fractional population difference, so rho 11 minus rho 22, between the lower and upper states. Suppose that in equilibrium, with no applied fields, no light shining on it, for example, that this difference would settle down to some value like this, some specific relative population of the upper and lower states. Then experience might tell us that because of mechanisms such as collisions with the walls of a box or with other atoms, or by spontaneous emission, such systems often settle back down again to this value with an exponential decay with some time constant. That is, if we start out in some value that's here different from this equilibrium value, then what tends to happen in many systems, just empirically, is that they will settle back down to this value sort of exponentially with some time constant t1. Then we could hypothesize that we could add a term to this expression we had for the time rate of change of the population difference to give us this kind of expression. If we were to turn off the optical field, the E here, so make E equal to 0, then this equation would actually describe a settling down of the population difference to this value exponentially. It's a simple differential equation that would give exponential decay back down to this equilibrium value. And it would have a time constant t1 for doing that. So we're simply hypothesizing, based on our experience with many systems, that if we turned off the excitation, then the population difference would settle back down again to its equilibrium value in an exponential fashion with a time constant t1. We have to consider a similar process also for the off-diagonal elements of the density matrix. For example, as in this equation here. And to understand this, we need to understand the meaning of the off-diagonal elements, rho 21 and rho 12, which we remember are defined with a relation of this form. So in general, a density matrix element looks like this, and in the case of off-diagonal elements, U and V are not the same, and so we're looking at an ensemble average here of the product of these two coefficients over all of the different possible states J in our mixed state. Within any given pure state J, this product is in general oscillating. If we have expanded in energy eigenstates phi u and phi v of the unperturbed system, there's a time dependence, an exponential of minus I EUT over h bar built into this coefficient, and a similar one built into this coefficient, the plus sign here because this has got a complex conjugate. So the product here of these two in general has an underlying oscillation of this form. As time evolves, the system can get scattered from a pure state J into another pure state K with some probability, possibly even a state in which rho 11 and rho 22 are unchanged. That is, for scattering from state J into state K, maybe it makes no difference to the populations here of these states, but in which the phases of the coefficients, these ones here, are different. At any given time, therefore, we may have an ensemble of different possibilities for the quantum mechanical state, all possibly with different phases of oscillation in that time-varying factor. In our mixed state, then, if we have sufficiently many such random phases that are sufficiently different, then the ensemble average of a product like this, for different u and v, that is, this ensemble average here, will average out to 0. But this ensemble average is simply the off-diagonal density matrix element. Hence, off-diagonal elements contain information about what we could call the coherence of the populations in different states, the extent to which they are aligned with one another in phase. The processes that scatter into states with different phases can be called dephasing processes. The simplest model is that dephasing processes cause an exponential settling of any off-diagonal element to 0, with some time constant typically called T2 to distinguish it from the T1 that we had for the population difference. Hence, similarly, we postulate adding a term like this to this equation we had for the rate of change of ρ21. Then we would obtain instead an equation like this one. So we've added in this term, we just made this up, postulated that this might be a good way to understand what happens in these systems. So if we were to turn off the optical field here, this term would be 0, and then we would have that d ρ21 by dt had this minus I omega 21 ρ21 in it, and then a minus ρ21 over T2. That would correspond to a system that was oscillating approximately at frequency omega 21 in its off-diagonal density matrix elements, and decaying exponentially to 0 with a dephasing time constant T2. So that's what a differential equation like this, with this term 0 and this I omega 21 ρ21 and this minus ρ21 over T2, that's what it would correspond to in terms of the behavior.
With the addition of this population relaxation time, commonly called T1, and this dephasing time, commonly called T2, we've moved beyond our previous Schrödinger equation. We are making new physical assumptions when we add these ideas. It's true here we've added in these relaxation processes without any real fundamental justification. We have no real guarantee that this approach will work, and there may well be situations where it doesn't. We are really just hoping that this addition of these exponential relaxations will be a useful model for actual physical situations. We've not derived these relaxations from any specific microscopic model. We're just guessing that the interaction of our quantum mechanical system with the rest of the world, which is possibly a very complicated world, can nonetheless be described well enough by introducing these relaxation processes. So, note we have no fundamental model here for deriving the numbers T1 and T2. Indeed, we may just have to measure them experimentally. Of course, we could make some models that would allow us to estimate what T1 and T2 should be in some situation, and this can be done. But we should be clear that, at least as we are introducing them here, we have no particular justification for doing this, and no particular method for estimating these numbers. The good news, however, is that this approach works quite well in many situations. It does give us at least a reasonable starting model, and we can use that model for handling the effects of interactions with the rest of the complicated world around our specific quantum mechanical system of interest.